Now that we are convinced we are going to do optical communication because the channel does not pose any limitation on higher frequency transmission, we will now see how do you do digital modulation for optical fiber. So, can you recognize what this equation is about? What does this represent? This is an electric field propagating along the positive z direction with a frequency omega c, angular frequency omega c. So, this is 2 pi fc, where fc is in hertz, having a specific phase phi, right, and E naught is the amplitude of the electric field. This E represents the direction of the electric field. What do you call the direction of electric field as in optics? Polarization, right. So, this represents the polarization of the electric field. Now, we have moved into optical communication, right. So, we did modulation, then we said digital is better, and then we said how to pick the carrier frequency, and now we are saying we will move to optical communication because of the fact that the course is about optical communication, okay. And all what we are talking about now onwards is going to be for optical carrier frequency, not RF, not microwave. Now, we will talk about specific digital modulation formats that will work for optical communication now. If you modulate the amplitude depending on your 1 or 0, you get ASK. We have already seen this. It is also called OOK. So, I keep my amplitude on or off depending on whether I have a 1 or a 0, that is ASK. If I change my carrier frequency, if I have a way of changing my carrier frequency, which means I have to change the color of my light, right. If I change the carrier frequency depending on whether it is a 1 or a 0, I get FSK. So, this is just to represent what ASK or FSK mean. See, for instance, the baseband signal. Let us say the baseband signal 1, 0, 1. This is what you want to transmit, this is what you want to modulate, and your carrier frequency right now, what is the frequency of this? If you, the moment you say we are talking about optical communication, so this frequency is terahertz, several terahertz. So, this TB is your duration of 1 bit, which is your bit slot. This is not to scale. You will have, if you were to put it in scale, you will have multiple oscillations of this red within 1 bit slot. This is just to for representative purpose. The carrier and the baseband time scales are not to scale with respect to each other, but this is what you would do in case of ASK. It is high and 0 when the digital signal is 0. As we discussed earlier, for FSK, you would say 1 will represent a high frequency, 0 will represent a low frequency. So, high frequency and low frequency. I will need a way to switch between high frequency and low frequency. Or it is like saying I will need a way to switch between, let us say, blue color for high frequency and a green color for low frequency, right. As the bit that you want to transmit keeps changing, you will keep changing the color, that is FSK. Now, the third way of doing it is change the phase as a function of the input bit. I could either change the amplitude or change the frequency, or I can change the phase phi. For instance, let us say I want to transport 1 0 1 1. I represent 1 as a phase 0, I represent 0 as phase pi. I mean, that is my way of representing. I can choose, so long as the transmitter and the receiver understands this coding, you can choose anything. So, I could choose 0 as 1, pi as, or I could choose pi by 2 and 3 pi by 2. I could choose any two different phases. I would keep the two phases as opposite to each other, just like 1 or 0. I would use 0 or pi as far as the phase is concerned, pi phase shifted apart. the envelope remains constant. At the end of the bit slot, the wave that was supposed to go this way, you see a phase jump here. Here again from pi to 0 it has to change. So, the wave that was supposed to continue this way, it actually got a pi phase shift. Here there is no phase change, so the wave is continuing as it is. So, this is how one would visualize a PSK, phase shift keying. Okay. Now, traditionally until almost 10 years ago, this was the only scheme that was used in optical communication. People did only on-off keying, and to be technically correct, they were not switching amplitudes, they were switching intensities. Now, what is the difference between amplitude and intensity? Mod square of amplitude is your intensity. So, it is as good as saying I turn my light on and off. That is why it is called on-off keying, right. You are take an LED or a laser or even the light bulb, make it on and off at the same rate as at which you want to communicate. That was intensity modulation, right. So, we say ASK, but what we were actually doing is intensity modulation. Until many years, and for so many years we were doing only intensity modulation, which is why all these traditional books on optical communication will talk only about intensity modulation unless you pick a recent book. Okay. FSK is not usually used in optical communication. Even today FSK is not an option. The reason being, it is very hard to switch frequencies of laser source. It is not that it is not possible, it is possible, but it is much harder than switching amplitudes or switching phases. We can switch phases much more easier than switching amplitudes. We will learn how to do switching of amplitude, drive current to the LED on and off. That is good enough for intensity modulation. Phase modulation we will see how to do that, but FSK we will not do because that is not an easy thing to do in optical communication. The same modulation we can do a constellation representation. So, let us take on-off keyed data. Your conventional representation is when the bit is high, high bit is bit 1, you say the signal S of t is E naught. When the bit is 0, when you have low bit, S of t is 0, high and low. What is the constellation representation? Suppose you write this process mathematically as a complex number, right. So, this is complex number 1 plus j times 0, there is no complex part, and this is 0 plus j times 0. I am just representing my resultant as a complex number. And just like in your Argand diagram, you have the x axis as the real axis, y axis as your axis that represents the imaginary part of the complex number, right. So, you call this as I and this as Q. In phase component, quadrature phase component, right. We will talk more about in phase and quadrature a little later, but let us take this x as I and y as Q. How do I represent these two states? The possible states are, I would have 1 plus j0, so which means it is on the x axis. I would have 0 plus j0, which is here. These two dots that I am putting are your constellations. So, in OOK or in ASK, the constellation looks like two dots on the x axis. There is nothing on the y axis. Why is there nothing on the y axis? Because there is no imaginary content here, because you are not doing anything with phase. So, there is no imaginary part, okay. You are just changing only the amplitude of the signal. So, you have 0 and you have these two. So, how do you make a constellation diagram? Let us say you have the freedom to look at the incoming data stream. All what you need to do is find out what is your bit duration. Within the bit duration, you find whether your amplitude is 1 or your amplitude is 0. Whenever your amplitude is 1, you put a dot here. or rather you put a dot corresponding to the amplitude of whatever you received, and you put a dot corresponding to, you keep doing that for every bit that you receive. So, sometimes you may receive a 1, sometimes you may receive a 0. So, you may get this or you may get this, and it is not necessary that you may always get the same amplitude. You may get something like this, you may get something like this, you may get something like this. So, what you will get is something what I am showing as a spread constellation, because every time you receive a bit, if it is a slightly non-ideal channel, if it is an ideal channel, everything is very ideal, I will always get the same amplitude. But if I have noise in the system, the constellation will start spreading. If there is too much noise in the system, what happens? My one level, let us say in your digital logic, one level represents what voltage? 5 volts, let us say. Sometimes you may get, if it is very noisy, the channel is very noisy, you may get 4.8, you may get 5.2, you may get, there will be a distribution. So, depending on the distribution, the constellation will start spreading. Okay. It is important to understand the concept of constellation, because all the impairments in the fiber, in the receiver, we will now talk in terms of how the constellation is spreading, right. So, the constellation is spreading in this direction, it means that the amplitude is changing. If the constellation is spreading in the angle direction, you say that the phase is changing. Of course, in OK there is no concept of phase. Okay. Now, if you were to do BPSK, binary phase shift keying. Binary phase shift keying means there are two possible phase levels. Those two possible phase levels, you can decide whether it is 0 or pi, you can decide whether it is pi by 2 or 3 pi by 2, you can decide whether it is pi by 4 or pi by 2 plus pi by 4, right. You can decide what those two phase levels are, and because there are only two phase levels, you would keep those two phases pi apart, so that they are very distinct from each other. Now, BPSK would mean binary phase shift keying. So, let us say bit 1 is represented by a phase pi and bit 0 is represented by a phase 0. How does the constellation look like? Now, look at the amplitudes now. Amplitudes are not changing, it is only the phase that is changing, which means the complex number representation for this, if I say my E naught is equal to 1, here also I had assumed E naught is equal to 1, that is why I got 1 plus J0. If I say E naught is equal to 1, what I would get is, in one case I would get, this would be 1 plus J0, and what about this one? It is minus 1 plus J0. So, these are your constellation points. So, when you move from OK to BPSK, what really happened in your constellation? They became farther apart. So, right from this point, you can intuitively say which is more resilient to noise? It is farther apart, so you have more noise resilience, assuming there are no other constraints for BPSK. Okay. A BPSK transmission, when you are trying to put that dot, remember we said here that let us keep receiving all the digital information and try to put a dot whenever we are receiving a 1 or a 0. Here, what are we trying to extract? How does the BPSK constellation timing diagram looks like? Is there any change in the amplitude? It is a constant envelope. You will not see any change in amplitude. You will have to detect the phase at every interval of bit slot. So, you need to have a phase detector, and the phase detector is going to tell you whether you received a 0 phase or a pi phase, and there could be an error in phase depending on the noise in the channel. The noise could be in transmitter, receiver, channel, etc. So, that error in phase will come out as this angle, right. So, you understand that error in phase will appear as an angle, error in amplitude will appear along the, error in amplitude is going to appear along the horizontal direction. This is going to be useful later on when we talk about signal to noise ratio, and as you are increasing noise, what happens, what does a EDFA or an amplifier do to the constellation. We will talk with reference to the constellation. Okay. Now, how can we squeeze some more? What are we trying to squeeze? We are trying to squeeze some more bits in one duration, bit duration. Here what did we do? Every duration, every bit slot, we transmitted only one bit. Question we are asking is, keeping the bit slot the same, can I squeeze some more bits? Can I put in some more bits? And the hint is, you see, we are using only 2 amplitude levels in the constellation. Can I not use more than 2 amplitude levels? You are using only 2 phase levels in the constellation. Can I not use more phase levels in the constellation? So, that is how you are trying to squeeze more bits in one bit slot. So, how are we going to do this? To squeeze more, we need to code the bits into what are called as symbols and transmit the symbols instead of transmitting the bits. So, we will talk about bit rate, we will talk about symbol rate. Bit rate will be in bits per second. What we calculated earlier, 64 kilobits per second. That was assuming that every slot is carrying only 1 bit of information. This one we will talk in terms of baud rates, symbol rates or baud rates. Depending on how we are coding the bits into symbols, there will be a unique relation between the baud rate and the bit rate. So, for example, let us say I want to transmit this sequence which is on the top. Okay. If I were to do 1 bit per second, bit per bit slot, I would code it as, I could do either OK or PSK. I would say this is 0, then 0. So, I will, if it is OK, I will transmit a 0, then I will transmit a 0, and then I will transmit a 0, and then I will transmit a 1, and so on. But instead, what am I trying to do now? I am trying to squeeze more bits in one bit slot. So, I decide that 0, 0, let me represent by symbol A, 0, 1, let me represent by symbol B, 1, 0, let me represent by symbol C, 1, 1 represented by D. So, instead of 2 unique values that I am transmitting, now I have 4 unique values I need to transmit. I should be transmitting either an A or a B or a C or a D. And each of the symbol is representing 2 bits. So, this is coding with 2 bits per symbol. So, if you talk in terms, there is a sample calculation done here. Let us say my time slot, the TB in which I am transmitting the information, let us say it is 50 picoseconds. I am transmitting, let us say 1 bit per slot. What would be the bit rate? In 1 second, how many bits can I transmit? 1 divided by 50 picoseconds. And that will come to be 20 gigabits per second. Now, there is no difference between bit rate and baud rate here because I am transmitting 1 bit in every symbol. But now, I can transmit, I can get the same bit rate of 20 gigabits per second. If I do 2 bits per symbol, I can afford to have a longer bit duration, twice as longer as the previous case, and achieve the same bit rate. The baud rate has reduced, but the bit rate remains the same. Other way of saying is that if I maintain the same time slot, what would be my data rate now? Bit rate will become twice because I encoded 2 bits in 1 symbol. Okay. How to do that we will see, but by converting bits to symbols, I can basically increase the data rate for a given bit slot. What is preventing us from using only 4 symbols, 4 unique symbols? Actually nothing. Instead of doing this, I could also do, so here I have used 2 degrees of freedom. I could now say that 0, 0, 0 represents something, 0, 0, 1 represents something, and I will have how many states? How many symbols then? 8 symbols. Or I could do 0, 0, 0, 0 as 1, 0, 0, 0, 1 as A, this as B. I can go all the way up to 16 symbols. So, what is the benefit of doing this? The data rates will increase for the same bit slot. Why are we interested in increasing the data rate for the same bit slot? So, what we also need to understand is that how fast you can signal this bit slot, that is decided by your electronics. The electronics can go on and off only at a specific limited rate. The state of the art electronics today is probably at 96 gigabaud per second. We are talking about here already 10 or 20 gigabaud. State of the art electronics is 96 giga. So, even with 20 gigabaud, if I have 1 bit, I can only transmit 20 gigabits per second. So, with 100 gigabaud, I can transmit how much? 100 gigabits per second. And I already told you that the current standard for optical communication is 100 gigabits per second. And 100 gigabaud electronics is only in certain very specific nice labs. It is not commercial, or it is not available in plenty at low cost and things like that. So, how are we able to achieve this? How are we able to signal 100 gigabits per second with a slower electronics? We are able to do this by bits to symbol conversion. Okay. So, as you move, this is exactly what I said, the bit rate carried by an optical communication system is not limited by the channel, it is limited by electronics, primarily by the electronics, because electronics can signal only at a specific, you can get only a certain minimum TB. So, you try to squeeze more number of bits in that TB. Okay. And as I said earlier, I will repeat, this concept was never used in optical communication until about 10 years ago.